have the chance to hear what he has to say, but also question him later. So without further ado, I'd like to invite Aubrey to the stage. So put your hands together for Aubrey de Grey.
Right, good afternoon, and thanks for getting back from lunch. Adam is making me work rather hard at this meeting. He's got me giving this talk, obviously, but also another talk tomorrow. I think it may be the last talk of the event, or the second last one, and also a panel this evening, at I think 7:30, the last thing this evening, with Natasha Vita-Moore. I of course, therefore, have been thinking a little bit about how to partition all of that time, and essentially the way I've decided to do it is to talk now about how it seems likely to me that we may, in the foreseeable future, be able to bring aging under true medical control, the same sort of level of control that we already have for most infectious diseases, and tomorrow evening to focus on why this is a good idea. That's a topic which comes up all the time, and which I think, even though this audience may be by and large sympathetic to the idea that it is a good idea, nevertheless deserves a good deal of scrutiny. Today I'm going to talk for most of the hour and leave maybe 10 minutes for questions towards the end. Tomorrow I'm going to make it much more interactive. I'm probably only going to actually give at most half an hour of actual presentation, and I'm going to try and leave therefore at least half an hour for discussion. Briefly this morning I actually thought about doing the talks in the other order, because I felt that there was so much to say about this topic in response to the first talk of the day. But I know that you're all going to, or at least most of you are going to be here throughout the conference, so I think I'll stick with what's in the programme and do the science talk now and the sociology and politics and economics and theology and everything else talk tomorrow. Okay, so first of all I want to start here. I want to talk about what the problem is, what the nature of the problem is, and in particular what the scale of the problem is. And the reason I thought I'd start here is because a lot of people get this wrong. Many people think of dying from aging as the best way that things can go these days. In other words, dying from aging as dying having avoided all of the things that we want to avoid, all of the specific diseases such as Alzheimer's or cardiovascular disease or type 2 diabetes or cancer or whatever that tend to afflict most of us as we get older. Some people, of course, do succeed in dying of what we sometimes call natural causes. And perhaps that is a little bit better than dying of all these other things. But the fact is that any death from any cause that is predominantly an age-related cause, in other words, affects people who were born a long time ago more often than it affects young adults, has to be included in any rigorous definition of death from aging. Because, I mean, think about it, how could anything be age-related? It must be because it is some aspect of the later stages of a process that goes on throughout life and is initially harmless and eventually causes ill health. And of course that process is aging. So if we take that rigorous definition of death from aging, then we get the sorts of numbers that you see on the screen now. Out of the people that die, the 150,000 people that die every day from all causes added together worldwide, 2/3 of them, 100,000 people every day die of aging. And of course in the industrialized world, where not many of us die of malaria anymore, it's a great deal higher than that, it's around 90%. So this is pretty unequivocally the world's worst problem, the world's most serious problem. And that's why I started working on it some time ago, when I began to realise that horrifically few other people were working on it. And the upshot at this point is that the foundation that has been created around my work, it's called SENS Foundation. We're based in California, and we're a charity working on the development of regenerative medicine solutions to the problem of age-related ill health. So, I'm going to explain to you, first of all, what that means, and then the details of how it's going. What does it mean? Well, in order to introduce that, I really have to start with two terms, the term regenerative medicine and the term aging. Most people have a pretty clear idea of what they think these terms mean, but actually both of them bear a certain amount of discussion and precision in their definition. First of all, regenerative medicine. I'm sure you've all heard of stem cell therapy, you all know more or less what it is. The introduction of cells into the body that can divide and differentiate to create cells that the body needs. There's also tissue engineering, the creation of artificial organs outside the body, which can then be used surgically to replace damaged organs in the body in just the same way as we might do a transplant from another person who recently died. But those are only two categories within regenerative medicine. Regenerative medicine as a whole needs to be defined more or less as you see on the screen now. Any medical intervention that restores the function of the body by restoring its structure at the molecular level or the cellular level or the whole organ level. I've talked already about the cellular level and the whole organ level, but molecular regenerative medicine is an equally valid concept, and it turns out that that's quite important as something to include when we come to see how regenerative medicine would be applied to aging. The other point is that regenerative medicine can be applied to aging simply because there is no particular reason why any particular type of damage should not be amenable to regenerative medicine. Damage that regenerative medicine is normally thought of as being applicable to tends to be acute injury, like spinal cord trauma or something. But the gradual, chronically accumulating damage that we see in aging is just as admissible as a target for regenerative medicine. All right, now what's aging? Well, I'm sure all of you have a fair idea in your own minds about what aging is. But the reason I want to dwell on this a little bit is because most of the definitions of aging that are out there are actually not very useful. In other words, they're not really very helpful to orient our thoughts around how we might actually intervene against aging. So that's why I like this definition. This definition is first of all a mechanistic one. In other words, it says how aging happens. And the way it says that is it basically says metabolism eventually causes pathology. So metabolism is the word that biologists use to encompass all of the processes that go on in the body that keep us going from one day to the next. It's just the normal operation of the human body. Pathology is the word I'm going to use to denote all the things that go wrong with the human body as it gets older. So metabolism eventually causes pathology. That's just a highfalutin way of saying that aging is a side effect of being alive in the first place. So of course you all knew that, but it's got to be in the definition. The thing that's a little bit special about this definition is the introduction of the word damage. The word damage, as I'm using it here, says in a very abbreviated sense how metabolism eventually causes pathology. The point about damage is that I'm using it here in this very precise sense to mean the set of intermediates between metabolism and pathology, the set of ongoing, lifelong changes to the molecular and cellular structure and composition of the body, which happen even starting before we're born, throughout life, and which accumulate. And the body is set up to tolerate a certain amount of that change, those changes to structure, changes to composition, but not an unlimited amount. And eventually the amount of alteration, the amount of damage, gets to a point that the body cannot tolerate, and that's when pathology starts to emerge and to progress. So that's the definition of aging that I like. And I'm going to talk now a little bit about why that definition is so useful. This is the first reason why it's useful. It helps us to distinguish the two major themes, the two major schools of thought that exist with regard to potential intervention in aging. Or shall I say, the two major schools of thought that have traditionally existed. I'm going to call those things the gerontology approach and the geriatrics approach. So the geriatrics approach encompasses essentially everything that we have today in the clinic to combat the diseases and disabilities of old age. And it can be defined as more or less treating those diseases and disabilities in the same way that we treat other diseases, like infectious diseases. Identifying the symptoms, trying to basically beat back the symptoms, to eliminate those symptoms from the body. And that's all very well with infectious diseases, but in the case of aging, as we can see from the definition, which of course I've got still here at the bottom, it's a losing battle. It's obviously not going to work. It's only going to be able to work a little bit. Because ultimately the geriatrics approach goes after the consequences of this thing damage which is continuing to accumulate. Pretty much by definition, the geriatrician's job is getting harder and harder as the patient gets older. So even in principle, however good we get at it, we are only going to be able to beat back the diseases and disabilities of old age modestly using this geriatric approach. Now, I'm by no means the first person to have made this observation, though I may be putting it in somewhat new words. And the realization that the geriatrics approach is futile has led people over the years to come up with what I'm going to call the gerontology approach, which essentially says, let's adopt the principle that prevention is better than cure, which of course it usually is, and let's try and instead intervene at an earlier stage in the chain of events, back here. What this amounts to is cleaning up metabolism. It amounts to trying to intervene so as to diminish, so as to reduce the rate at which metabolism creates these various types of damage, so that, of course, we will then postpone the age at which damage reaches this pathogenic threshold. And that sounds like a much better idea. And indeed it is. It's going to, there's no reason in principle why it should not quite substantially postpone the diseases and disabilities of aging. Unfortunately, there is a problem with it, a massive problem. Here's the problem. Metabolism is rather complicated. This is a simplified diagram of a small subset of what we know about how the body actually works, how metabolism works. And as you can see, it's a bit hairy really, and the idea of tweaking it, tuning it in some way so that the damage that it causes is less, without doing more harm than good by disrupting something we don't understand, is pretty daunting. It's pretty unlikely that we do that. But actually the problem is even worse. The problem is not just that this is a simplified diagram of a small subset of what we know about how metabolism works. The problem is that this is a simplified diagram of a small subset of what we know about how metabolism works, which as any biologist will tell you is utterly, completely dwarfed by the astronomical amount that we don't know about how metabolism works, even ignoring all the stuff that we don't even know that we don't know. So it's an idea whose time has emphatically not come, even if it might, in principle, in the long run, be a practical approach. All right, well that's all rather dismal. I've now comprehensively dismissed both of the approaches that seem to exist for combating aging. But of course, if that were the end of my story, then I wouldn't be standing here. So, what's the catch? Well, in order to introduce it, I'm going to talk briefly about cars. The reason I'm going to do so is because the human body is, of course, a machine. It's a very, very, very complicated machine, but it's still a machine. So, in principle, we ought, at least probably, to be able to identify hints as to how we might successfully postpone the ill health of the human body beyond what you might call its warranty period by looking at how we already successfully postpone the ill health of simple man-made machines beyond their warranty period. Alright, so let's look at a simple man-made machine. Let's look at this one. This car is more than 50 years old, and that of course is pretty unusual for a car. Most cars maybe get to 15 years before you junk them and get a new one. So how did that happen? Well, of course the answer is that this car was built to last a long time. Corrosion-resistant metal and really tough tires and all those good things. And that's very much the same reason why the human body lasts so much longer than the body of a dog, or a mouse, for example. We're simply built better. We have more sophisticated, inherent, inbuilt, automatic, anti-aging machinery than what those shorter-lived organisms have. So we last a lot longer. But that's not the whole story. There's another way in which cars can last a lot longer than 15 years. Here's a car that was built in the same year as the one on the previous slide, and it was not built to last. The reason it's lasted a long time is because it has been very, very, very well maintained. More comprehensively than most people maintain their cars. And sure enough, it's working just as well as when it was built. This shows us that, at least for simple machines, maintenance actually works. We can dramatically, perhaps indefinitely, postpone the ill health of simple man-made machines by maintaining them sufficiently comprehensively. And if we now translate that analogy back to the human body, we can see what it means. That there is a third approach that we need to consider. I'm going to call it the maintenance approach. So here, what we're doing is, rather than trying to slow down this process where damage creates pathology, or this process where metabolism creates damage, instead we propose to actually separate those two processes from each other by going in and periodically repairing this damage, not necessarily completely, but reasonably well, so that it doesn't get to the level of abundance that causes the pathology of old age. That's pretty interesting, and I think it's got a much, much better chance of success in the foreseeable future than either of the other two approaches. You can see why. It simply avoids the shortcomings I've pointed out, the difficulties with the other two approaches. First of all, you don't have this downward spiral of the geriatrics approach. Here what we're doing is we're targeting stuff that is the initial, ongoing consequences of metabolism. So in other words, it doesn't have accumulating precursors that intrinsically make the problem harder and harder as the patient gets older. But also it avoids the problem with the gerontology approach, because here we're not proposing to interfere in metabolism at all. We're proposing to let metabolism create damage at the natural rate, and then just go in and repair that damage periodically before it gets to the level of abundance that's bad for us, but after it's actually been created. So in other words, while it is not in any way participating in metabolism. And that gives us a much, much better chance of, in a sense, sidestepping our ignorance about metabolism and getting the effect we want without unintended side effects. So that's pretty good news. But it gets better. So far, of course, I've been very theoretical and abstract, and I haven't told you what this damage thing actually is. But here's a little bit about that. It turns out, or at least I believe, that all of the phenomena that qualify as damage, by the definition I'm using here, these intermediates between metabolism and pathology, can be classified into just 7 major categories. And here are the categories. And as you can see, these are bona fide, real biological phenomena. Cell loss. That means simply cells dying and not being automatically replaced by the division and differentiation of other cells. So the number of cells goes down and eventually that's bad for you. Parkinson's disease is a fine example of that during aging. You can have too many cells because cells are dividing when they're not supposed to, and of course that's cancer. You can have too many cells because they're not dying when they are supposed to. That's actually a phenomenon that a lot of people neglect, a lot of people forget about it, but it's very important, it turns out, in aiding of the immune system, among other things. There are these special parts of the cell called the mitochondria, which do the chemistry of breathing, and they have their own DNA, which accumulates mutations, and there's lots of good evidence that that's bad for us during aging in a variety of different ways, and the precise details are still somewhat elusive. There's accumulation of what I'm calling here intracellular junk, simply molecular byproducts of normal essential metabolic processes, which, for whatever reason, the body does not have the machinery either to break down or to excrete. So those byproducts simply accumulate inside the cell, and eventually they get in the way, very much in the same way that your house doesn't work so well if you don't take the garbage out for a month. It turns out that molecular garbage can also accumulate outside the cell in the extracellular space. An example of that is the amyloid that accumulates in the brain during Alzheimer's disease. And finally, the stiffening of the lattice of proteins that holds our tissues together, that's called the extracellular matrix. That matrix needs to be elastic, especially in certain places like the walls of our major arteries, and that elasticity diminishes over time due to certain chemical reactions that happen, called cross-linking. We need to fix that. So those are the 7 categories which I claim span all of the things that qualify as damage, that qualify as these intermediates between metabolism and age-related pathology. How can I make such a claim? Well, first of all, we can just look at what the body's made of. We can say, where are the long-lived structures, the structures that have the potential to accumulate damage? And we can get pretty much this list if we just do that. But also, we can actually appeal to history. We can note that there's actually been 30 years since anyone thought of a new category. All of these things have been discussed since way before I came along. In the gerontological literature and the community, there have been major topics of research and study, and you would think that this list would have been extended in the past 30 years if there were any extended to do. So that's of course a circumstantial argument, but I think quite a compelling one. So this is pretty good news. We can define the problem in terms of these 7 sub-problems, and that, of course, is always a great first step when it comes to addressing a really difficult technological challenge. But it gets better, because it turns out that we can actually describe in a lot of detail not only what the problem is, but also how we have a respectable chance in the foreseeable future of actually solving each of these problems. So on the left-hand side of this table, you'll see the same list that you saw on the previous slide. On the right-hand side are the proposed solutions to these things. At the top, you can see we're talking about stem cell therapy. This, of course, is exactly what we do to solve the problem of cell loss. I mentioned Parkinson's disease earlier. Cells in the substantia nigra, a special part of the brain that creates a chemical called dopamine, turn out to die a lot faster than neurons in the rest of the brain, and they're not replaced, and that means that the number of cells goes down, and we don't make so much dopamine. Most people lose about 20% of their dopaminergic neurons from that part of the brain during life. Some people who are unlucky lose a lot more than that, and that's why they get Parkinson's disease. And there are various treatments for Parkinson's disease that are in use today and that don't work very well, or at least not for very long. But there's also work going on to develop stem cell treatments for Parkinson's disease, and that work is in a relatively early stage, but it's in clinical trials. Sometimes it works, sometimes it doesn't, but when it does work, it works spectacularly. So that's definitely the way that we're going in terms of treatment for Parkinson's disease. Once we figure out how to do it right, Parkinson's disease has a good chance of seriously being a thing of the past. If we go down the list, the same sorts of things can be said. I've mentioned each of these things in the same order as before. I'll go through them in a slightly different order in the next few minutes because I want to highlight a few of them. I've already mentioned clinical trials against Parkinson's disease. There is actually an even greater degree of progress in clinical trials for this one down here, extracellular junk. I mentioned Alzheimer's disease as an example of where we see molecular garbage accumulating in the body during aging. Of course, in this case, it's in the brain. And the garbage is called senile plaques, made of a material called amyloid beta. Turns out that you can immunize against this stuff, and that will cause it to be engulfed by cells and destroyed once it gets inside the cell. And the first demonstration that this was a potential treatment against amyloid accumulation was only 13 years ago in mice, but and that's not very long by medical standards, but people were so excited by it that they moved very rapidly to clinical trials, and those trials are now in phase 3, which is the last stage before regulatory approval, and word has it that things are going rather well. So that's pretty good news. We are really getting there for some of these particular types of damage. We're not just slowing down their accumulation, but actually removing. And I'll come back to why that's so important later on. Now, all of the ones that I haven't highlighted in red here are, I completely concede, at a significantly earlier stage of development. But that's okay, you've got to start somewhere. Let's look at this one. The accumulation of what I'm calling death-resistant cells, cells that we have too many of because they're not dying when they're supposed to. So I've highlighted this one because it's making headlines. It's been something of a Cinderella among aspects of aging for quite a while. People haven't really paid very much attention to it, but that's beginning to change. And it changed quite a lot about 6 months ago when a paper came out that I'm highlighting here in Nature, in which it was just a proof of concept. It's not something that can be directly applied in the clinic by any means, but it's a big proof of concept. Essentially what happened here was the researchers created a mouse which on the one hand had a genetic modification that caused it to accumulate these death-resistant cells at an unusually rapid rate. And on the other hand, they had a second genetic modification which allowed those cells to be removed at any time in the mouse's lifespan by the administration of a simple drug. Now, the first thing was that when you didn't have that drug, when those cells were allowed to accumulate, the mice sure as hell got unhappy pretty early on in their lives. They only lived about half as long as normal, and this is what they looked like shortly before death. Not very good. But also, these researchers were able to show that those cells were, when those cells were removed, that the mice were a lot happier. they were able to administer this drug halfway through the mice's lifespan, and this is what the mice looked like at the same age if those cells had been eliminated. And there are a dozen or more different aspects of aging that were studied in this particular paper. This is just one representative example. It's looking at the thickness of muscle fibers, which is something that diminishes during aging. That's just one example. Lots and lots of things were checked out and were rejuvenated by this treatment. So even though, as I say, this is just a proof of concept, it's a very important one in terms of lending credibility to the whole idea of removing death-resistant cells as a feasible and effective aspect of treating aging. Now, I want to talk now a little bit about work that SENS Foundation is doing. We're a non-profit, we're a charity, and as such, we have the good fortune to be able to work on things that are very long-term, that are very early stage at this point, and therefore not necessarily of interest to the private sector. And one of them is the elimination of molecular garbage that accumulates inside cells. This is something that underlies some of the most important diseases of old age. It underlies cardiovascular disease, which is of course the #1 killer in the entire Western world. It also underlies macular degeneration, which is the major cause of blindness in the elderly across the whole world. So, what's the deal here? How can we actually address this? Well, I've put this somewhat runic 3-word description here, transgenic microbial hydrolases. Let me tell you what that actually is. Essentially, First of all, an elaboration of the problem. This is just the example of cardiovascular disease, where what happens is you've got cells in the walls of our major arteries, cells called macrophages, which start off as perfectly self-respecting white blood cells, whose role is to recycle detritus that has become stuck in the walls of the arteries. And they're very good at this, and they recycle it pretty well, but they get poisoned by contaminants in that detritus that they do not have the genetic machinery to process. Those contaminants are mainly oxidized derivatives of cholesterol, what are called oxysterols. And this is what they turn into. They turn into things called foam cells, which are basically sort of undead macrophages that have stopped working and are just sending out inflammatory signals. And the thing that goes wrong inside a macrophage that turns it into a foam cell is this thing here, the lysosome, which is the cell's garbage disposal machinery of last resort, and is an absolutely essential component of the detritus processing machinery within the macrophage. It gets poisoned, it can't do the stuff that it normally does do, processing normal cholesterol, for example, and this is the sort of result you see. And this is actually the first visible sign of an atherosclerotic plaque. When you get more and more of these, you get a bona fide plaque, and that's, of course, where heart attacks and strokes eventually come from. So this is what I mean by transgenic microbial hydrolases. Essentially, what we are hoping to do is to exploit a technology which comes from environmental decontamination, nothing biomedical at all. And that technology involves using bacteria to break down pollutants in the environment, chemicals which we want to get rid of. And bioremediation is a remarkable idea. It's a very thriving commercial discipline because it works really well against all manner of pollutants, basically against anything which is organic and energy rich, so that if bacteria can destroy it, then they can live off it, they can extract energy from it. Now, the proposal today, the proposal that we are exploring is not to inject such bacteria into the human body. That would probably be a bad idea for all manner of reasons. But what we are proposing to do is something a little bit similar to that, just one step removed from that. Essentially, there's a process in the human body, of course, that turns young people into old people, and that process eventually turns old people into dead people. But then there's a completely different process that turns dead people into decomposed people. That process, of course, is not encoded in our genome, it's encoded in the genomes of the microbes in the environment. And one rather useful observation that we can start from is the fact that these compounds that cause diseases like cardiovascular disease do not accumulate in environments that are enriched in human remains, such as graveyards. So we can infer that those substances are probably broken down by microbes in those environments. Here's a microbe which we are talking about. Now, rather than identifying those microbes and injecting them into the body, the proposal is to identify how those microbes are doing it, to identify what genes and enzymes they have that give them the capacity to degrade these substances. If we can do that, which is denoted in this way, then we can apply that knowledge, we can introduce those genes and enzymes into our own cells, and thereby counteract the process that turned young people into old people in the first place. So that's the general idea. Does it work? Well, we don't know for sure yet, but it's looking damn good. Here's the first step: find the bacteria. The way you do that is just the same as you do it in environmental decontamination. We do something called an enrichment culture, which essentially says you take a variety of different bacterial strains and you give them the substance you'd like them to break down, and you don't give them anything else to grow on. So there's selective pressure to actually break down this substance in question. And here we have a representative experiment in which 7 different strains of bacteria are being given this particular substance, 7-ketocholesterol, which turns out to be public enemy number 1 in atherosclerosis. And 5 of them can't do anything with it at all, so they're sitting down like lemons and nothing's happening. But 2 of them have a great time, and after only 10 days, the material's entirely gone. You don't even need a microscope to see the result, it's all very straightforward. So we're pretty damn good now at identifying bacteria that can break down the substances that we want to get rid of. We're also very good at figuring out how they're doing it, identifying the genes and enzymes in question. This is one way we do it, it's called mass spectrometry. What we do is we identify the breakdown products that are being created by the bacteria when they degrade the substance that we are giving them. And by identifying those breakdown products, we can deduce what enzymatic reaction had occurred, and from there we can infer, using bioinformatic approaches, candidate genes that may be involved. We've been very successful using that approach. Another approach is to do essentially subtractive expression analysis to identify which genes in the bacterial genome are upregulated when the bacteria are given the substance of interest, but not upregulated when they're given a similar substance that we don't want them to break down. So in this case, normal unmodified cholesterol, for example. Both of those approaches work really well. So that's great. The next step is to introduce those genes and enzymes into our own cells, into mammalian cells. And of course we start by doing that in cell culture in the lab. And that's actually pretty tricky, because we don't just have to stick the gene in. We have to modify it so that the enzyme is targeted to the right part of the cell and so that it still works. So I told you about the lysosome earlier, the place where most of the action is for the accumulation of molecular garbage. This here is a stain, acrid in orange, that shows you where in the cell the lysosomes are. This is a stain that shows us where our engineered gene has gone, or rather where the enzyme that is encoded by that gene has gone. And the fact that this is mostly yellow, this overlay photograph, tells you that the localization is happening appropriately, that most of our enzyme is going to the lysosome. So that's all good news. But of course that's only the first step. Now we've got to know, does it actually still work when it gets there? And the good news, and this is preliminary data, but it's going pretty well. Actually, the first paper that reports this work just came out about a month ago, so I need to update this slide and put the reference on. But the deal is that it seems to work. What this is showing is that if you give cells in cell culture a completely obscene amount of this toxic stuff, 7-ketocholesterol, then it doesn't matter whether they have this engineered gene or not, they get overwhelmed, so this background level of fluorescence shows that nothing's happening. All the bars are the same height. That says that cells that have the gene and the enzyme being targeted to the right place are no better off than the negative controls, which don't have the enzyme at all, or they have it targeted to the wrong place, or whatever. But if you look at these other columns, these are showing more modest levels of the toxin, and you can see that the right-hand bar in each case is significantly taller than the other bars. That tells us that when the enzyme is being expressed in the cell and when it's being targeted to the right part of the cell, the lysosome, the cells are protected from the toxin relative to how they are in these various negative control experiments. So that's pretty good news. It's early days, as I say, we've got to do a lot more of this, we've got to get a stronger result, and we have various projects underway to make that happen. But it's all going very nicely, we're pretty hopeful. Now, I'm not going to try and tell you that we're anywhere near the end of the road on this. This is a very long and elaborate and ambitious research program. I've told you about steps 1 through 4 on this list, But even once we've got steps 3 and 4 really working reliably, really working well, we've still got a bunch of work to do to make this all work in live animals, in actual mice, rather than just in cells and culture. I wouldn't be at all surprised if that takes us a couple of years at least. And it's only then that we're going to be in a position to move to clinical trials and actually see whether this works in human beings. So yeah, very ambitious, it's still pretty early stage, but that's fine, that's perfectly okay, because the fact is, at the moment, these diseases, like cardiovascular disease, macular degeneration, are pretty much untreatable. We've got therapies that can very modestly postpone them, but ultimately they're just tinkering around the edges. They do not address the crux of the problem, and therefore they can only very modestly postpone these terrible progressive diseases of old age. And nothing's coming down the pike that's significantly better. So we've got to think out of the box and do these radically different experiments, develop these radically different therapies if we're to have any chance of seriously bringing these diseases of old age under control. All right, well that's the hardcore biology of this talk. I'm going to spend the next 10 minutes or so talking about the longer term. Of course, this is the Humanities Plus conference, in which a lot of us think very much about the longer term future of technology and where it's all going. And there's plenty that I've published and thought about and written about in relation to that. So I'm going to summarize some of that right now. I often talk about this regenerative medicine approach to aging as being a way of defeating aging altogether. And some of you will have noticed earlier on, when I put this table up, that the title did not really talk about defeating aging altogether. It simply talked about adding 30 years of additional healthy life to people who are already in middle age. 30 years is, nothing to sneeze at. That would be very nice, but it's not defeating aging altogether. So, what else have I got to say? Well, I'm going to talk about that now. I told you earlier that it's impractical, for the foreseeable future anyway, to hope that we will generate therapies which will significantly slow aging down. That was what I was calling the gerontology approach, cleaning up metabolism so that the damage of aging is generated at a slower rate. But let's suppose for a moment that I'm wrong about that. Let's suppose that we did have such a therapy. What would it actually look like in terms of extension of life? This is a very schematic, obviously, very abstract summary of what it would look like. So the red line here is supposed to denote normal aging. On the x-axis we've got age, on the y-axis we've got reserve. Reserve is simply the reciprocal of damage, the amount of additional damage that you can afford to accumulate before things start going wrong. So the red line simply says that at age 0 you've got not much damage, lots and lots of reserve. Time goes by, aging happens, you accumulate damage, the reserve goes down, and eventually you hit this frailty threshold, this horizontal dotted line, at which point pathology starts to emerge and progress and you're not long to this world. So the blue line represents a halving of the rate of accumulation of damage, starting here at, let's say, age 30. And as you can see, you get a whole chunk extra healthy life, and below here, the unhealthy life is probably not significantly extended because once pathologies start to happen, they spiral out of control. They exacerbate each other. It's all basically a vicious cycle after that. And therapies that slow down the accumulation of damage probably don't make very much difference to the rate of progression. Okay, so all that's good. You've got an extension of healthy life. You haven't got a significant extension of unhealthy life. Fine so far. Problem is, you have to start at age 30. If you start later, if you start, let's say, at age 60, then the amount of additional healthy life you get is correspondingly a lot less. Okay, that's pretty obvious. Is that it? Well, maybe not. Think about this. Supposing that you have those therapies that halve the rate of accumulation of damage, but then before our hero gets to the frailty threshold, the therapies are further improved in their comprehensiveness, so that we halve the rate again. So it's now a quarter of the natural rate instead of half the natural rate. Then of course you get some more increase in healthy life. That's not bad. Of course it's still not quite as good as if it started early, but unfortunately those of us who were already age 60 before the therapies have been developed don't have the option of the blue line. Bit of a shame. Now let's consider the option of these repair therapies, this maintenance approach that I've been talking about. That's what it looks like. the pink line. Here we're comparing like with like. I'm comparing two people at age 60. One of them gets these retardation therapies that slow down the rate of accumulation of damage by a factor of 2. And the other one gets repair therapies that simply repair half the damage. They actually eliminate half the damage. So this is what happens. You get this person rejuvenated back to here. And of course the therapy can be applied repeatedly, and that's what you get. Now, as you can see, you do get diminishing returns, because when I say we repair half the damage, that's because some damage is easier to repair than others, and the difficult damage that isn't being repaired by these therapies is continuing to accumulate unabated and eventually tips our hero over the frailty threshold anyway. But as you can see, the amount of extra life you get is far more with the repair approach than with the retardation approach. And again, it's extra healthy life. So that's pretty good news. So now I've given you two ways in which this line here, this simple approach for our 60-year-old, could be improved. Let's put those two approaches together and see what we get. This orange line is what we get. Here what I'm saying is, number one, we're talking about a rejuvenation approach, a repair approach, rather than a retardation approach. And number two, we're looking at what happens if we improve the quality of those therapies over time as a result of progressive technological progress, biomedical research. What you get is our hero comes in for their second rejuvenation therapy here, and they get therapies that repair the easy damage again, of course, but they also repair some proportion of the difficult damage. So third time they come in again, they get a bit more difficult damage that can be repaired. And as you can see, this is qualitatively different from all the other situations. In all of these cases, you eventually hit the frailty threshold, but here you don't. However long this goes on, however long the individual lives, they continue to get biologically younger as they're getting chronologically older. They never get anywhere near the pathologies of old age. So that's why we can seriously talk about defeating aging altogether, why we can talk about indefinitely postponing the ill health of old age. The only thing that this relies upon is sufficiently rapid improvement in the comprehensiveness of these technologies, so that this amount of rejuvenation the second time leaves the person biologically younger than they were after the first rejuvenation, when they were chronologically maybe 20 years younger. We have to have sufficient rate of improvement to the technologies so that the long-term trend here is upwards rather than downwards. And that required rate of improvement is such an important concept for our future that I gave it a name. I called it longevity escape velocity. It's written down here, the definition, the rate at which these rejuvenation therapies need to be improved following the achievement of that first step, those first generation rejuvenation therapies that give maybe 30 years of extra life, in order to stay one step ahead of the problem and make sure that the damage stays below the frailty, the pathogenic level. So the question then is longevity escape velocity realistic? Are we likely to be able to actually improve therapies fast enough? Well, I want to suggest to you that actually it's vanishingly unlikely that we would fail to do that. It's virtually certain that we would do it. The best and most direct evidence that I have for that is a computer simulation that I did a few years ago in partnership with a colleague in New York. And that simulation took the definition of aging that I've been talking about for this afternoon, and we simply modelled it in such a way that we could then superimpose a schedule of introduction and improvement of these rejuvenation therapies. And it's all published, of course, so I can send reprints to anyone who wants, but the bottom line is here. These are survival curves. So a survival curve is simply a graph showing what proportion of a given initial population is still alive at a given age. So the black line here is not a simulation. This line here is actual real data, showing a population, I think it was American males in 1999, something like that. And as you can see, everyone's alive, of course, by definition, at age 0. Hardly anyone dies until age 50 or 60, then they start dropping like flies, and hardly anyone gets past 100. So that's a normal survival curve. The blue line here, this dark blue line, as you can see, very close to the black line. The dark blue line denotes a simulated population whose intrinsic risk of death at any given age is the same as in the black line, but in this case they're getting these therapies that I was speaking about, these rejuvenation therapies. However, they're only starting to get them from the age of 80. So that, of course, is why the two lines are coincident down to here, because half the population is already dead by the age of 80. And after that, you get a bit of improvement, but only a little bit. You know why it's only a little bit? Simple reason. I've been telling you the whole time. This is all about health. Anyone who thinks I work on longevity is wrong. I work on health. And any longevity benefits that we might actually see as a result of the medicine that I'm talking about today will be a side effect, a great side effect, but still a side effect of health benefits. So, of course, these people at age 80 are already mostly not doing very well, and they're not very healthy, and the therapies are just not good enough to overcome that. So these people get a little bit of improvement, some of them, but ultimately, every year that goes by, they've got a relatively high risk of death as a result of not being very healthy, and they just statistically haven't got any chance to speak of getting out the other end. But now, look at this line, this grey line. This line here is exactly the same simulation as the dark blue line, with one difference. Namely, these people are given these therapies starting 10 years earlier, starting at age 70. And as you can see, it's very much the same story for a while, but eventually those people who are lucky enough to get through to about, let's say, age 150, have really started to benefit from these therapies getting the upper hand, and starting to actually overcome the damage and make people biologically younger again. So as you can see, 10% of these people really get to a point which can unequivocally be described as longevity escape velocity, where the risk of death from aging has gone away completely. These graphs don't show the risk of death from causes other than aging. If you're 60 when the therapy starts, then that's this line here, the brown line, and nearly half the population do it. But now, why is this interesting? Why is this so persuasive to me? Well, all of you know, those of you who work with computers anyway, that one can simulate anything. You can get any answer from a simulation. So in theory you might think, well, that's not a very strong argument. I know that as well as you do. And that's why, in this simulation, I decided to make it very hard for me to get the answer I wanted. What I did was, I chose parameters that are ludicrously, insanely pessimistic. Look at this up here. What I said was, let's presume that the therapies in question, these rejuvenation therapies, are doubled in their efficacy only every 42 years. So, double in efficacy, that means halving the proportion of damage that we can't yet repair. That's just completely crazy. 42 years. Now think about how long that actually is. That's the amount of time that went by between Lindbergh flying across the Atlantic, first solo flying across the Atlantic, and Concorde first flying across the Atlantic, 1927 to 1969. And that was last century. You know, obviously things are moving faster this century anyway. So it's completely ridiculous to presume that we would only double the efficacy of these therapies in that enormous interval of time. And yet, even if we did only double in that period of time, we still unequivocally get longevity escape velocity. So that's what leads me to believe that we are completely certain to achieve and to maintain longevity escape velocity once we get those first generation therapies that give just a couple of decades of additional healthy life. So what does this mean? Well, I told you a moment ago that I don't work on longevity, I work on health, and longevity is a side effect. But nevertheless, everyone cares about longevity, so I have to give straight answers to straight questions. The world record lifespan at the moment is 122. A wonderful lady named Jeanne Calment, who died 15 years ago in the south of France. She had a wonderful sense of humour as well. On her 120th birthday, when she was asked for the billionth time, "What's your secret?" she said, "My secret is I gave up smoking at 117. Yeah, she was good like that. Anyway, so the thing is, that's 122. Actually, we won't get anyone aged 150 until we achieve these rejuvenation therapies, these first generation ones that add a couple of decades to people's healthy life. But what I've explained to you in the past 10 minutes is that once we've done that, we will have done the hard part. Keeping going after that will be very much more straightforward. So that people only a little bit younger than the first person to get to 150 will be living to 150 in droves, and most of those people should be able, so as long as they have access to the state-of-the-art therapies at any given point, they should be able to avoid aging indefinitely. And that's why we can talk about ages like 1,000. 1,000 is actually a quite conservative estimate of how long people would live today if aging didn't exist. You can get that number just by looking at statistics for how often people die in early adulthood. If you reach your 26th birthday in the industrialized world these days, then your chance of not reaching your 27th birthday is less than 1 in 1,000. So, of course, if you maintain that, then your half-life is going to be in 4 digits. And as I said, that's a very conservative estimate because, of course, as time goes forward, we're going to be reducing our risk of death from causes other than aging as well. So that's sort of answer we can get. And people obviously get terribly exercised when I talk about 1,000-year lifespans, but the fact is, it's an inescapable conclusion from the logic I've just given you. Again, it's all about health. People get so confused about this, and they ask things like, so this morning, those of you may have remembered that the question was asked, how long do you want to live? And people said, do you want to live to 80, 90, and so on, and I shouted out that that was the wrong question. It is the wrong question. The reason it's the wrong question is because it's not something you need to have an opinion about. You know, it's like having an opinion about what time you want to go to the toilet next Sunday. You know, I mean, you know that that's a dumb thing to have an opinion about because you know that you're going to have better information on which to make that decision nearer the time, yeah? It's exactly the same. It's exactly the same. I haven't the faintest idea whether I want to live to 100. How ridiculous to have an opinion about that. But I do want to be able to decide whether to live to 100 when I'm 99, rather than to have that choice progressively removed from me by my declining health. Now, saying that, I think it's quite likely that I'm going to want to live to 100 when I'm 99, because the fact is I know that I don't want to die anytime soon, and I know that a major determinant of why I don't want to die anytime soon is the fact that I'm healthy, and therefore able to actually, get the most out of life. But there again, if I stay healthy, I'm not going to worry about how long ago I was born. I'm just going to carry on not wanting to get sick, and I'm going to carry on not expecting to want to die, as long as I don't get sick. It's as simple as that. Anyone who thinks that it would be a bad idea to combat aging, well, why don't I just talk about that tomorrow? You can come along and hear what I've got to say about that. But anyway, so yes, it's all about health. And when I say health, I really mean health in every respect. I mean looking, feeling, and functioning exactly as well, however long ago you were born, as you did in early adulthood. Seriously being able to keep up with your granddaughter on the dance floor. Now people will say all these things, they'll say, well, we put all the people, they worry about sustainability and the environment and so on. They'll say, well, I wouldn't want to live forever. They'll say, it won't be in time for me. I've got plenty to tell you tomorrow about what I think about those reactions. So I'm not going to tell you now. I'm just going to say, if you want to know more about this, I'll be around all today and all tomorrow, so you can ask me plenty of questions, as well as right now in the Q&A. But if you want to know more than that, I do encourage you to get hold of this book, which came out a few years ago now, but it's still pretty up to date. It's not a book for specialists. It doesn't rely on any, knowledge of biology jargon or anything. However, it is very detailed. Those biologists who have read it have certainly never complained to me that I cut any corners. It's got everything. So it's very heavy going if you're not a biologist, but if you're willing to take your time with it, you will learn an awful lot about how this is actually realistic and how rapidly it's moving forward. I emphasise there that it's worthwhile for you to get the paperback edition because that came out a year after the other one. And in that 1 year, so much happened that we had to write an entire full-length chapter just to cover those 12 months of progress that was made in developing these various technologies that I've summarised today. So I'll stop there. This is the foundation. There's our website and my email address. Of course, you're always welcome to go to either of them. But in the meantime, I'm very happy to take questions for a few minutes. Thank you. I don't know who has the roving mic, but I imagine somebody does. I see lots of hands. I don't see a roving mic. Who's got it? The person who used to have it has just walked out of the room. Anyone see Adam anywhere? Okay, if we haven't got a microphone, you're just going to have to shout. First person first. Yeah, we're going the red sweater. That's you, yes. Are you asking questions? Oh, you're not?
There may be a microphone there.
Oh. Well done. All right then. Yeah, you do. Pass it to anyone you like. Pass it to anyone you like.
Okay, a couple of comments. Firstly, doubling every 42 years.
Speak up.
Doubling every 42 years means that the residue that you can't solve is supposed to halve every 42 years.
That's right, yeah.
I did wonder about that. But the thing I was going to ask mainly is, what happens to memory?
Sorry, what happens to memory?
After 1,000 years.
Okay, so, what happens to memory if we live a lot longer? Well, in order to answer that question, the first thing we have to think is, what happens to memory today as we get older? And the answer is, it's at some kind of equilibrium. Memory, of course, is stored holographically. It's not like one fact in one synaptic connection. And when we recall a memory, that process reinforces it. And when we learn something new, that goes in over the top of everything else. So memories that we have are gradually lost and then restored and reinforced when we recall them. So the things we forget are things that we're not recalling. Now that sort of doesn't bother me. I mean, I only remember half the names of the people I was at school with, and that's fine really, because they don't matter to me. So we're at equilibrium already. It seems to me that that's likely simply to continue to be the case. Of course, there are other things that go wrong with memory in old age today, but that's precisely because of the structural, compositional changes to the brain that we're proposing to repair here, just as we're repairing the rest of the body. So I don't think there's really going to be any difference to the way the memory works. Next, who's got the microphone? Go on. Whoever's got the microphone, speak up. Oh, you got it.
Okay, well, I have a question then.
All right.
Two things, just for everyone's benefit. When you get the microphone, if you could just hold it like that. If you touch the bottoms, the buttons, bad things happen. So, my question is, can you talk about macular degeneration and what goes wrong there?
Okay, so macular degeneration is very much like cardiovascular disease in terms of what sort of thing is going wrong. In this case, the type of material that accumulates is very different in terms of its chemical structure. We're not talking about oxidized cholesterol this time. We're talking about chemicals called bisretinoids, which are created by a chemical reaction between photoreceptor material that's involved in the actual chemistry of sight and cell membranes. Those bisretinoids, again, are refractory to degradation by the cells in the back of the eye, in the retina, and so those cells, the retinal pigmented epithelial cells, as they're called, they fill up with this stuff, and once they get too full, the cells just don't work so well and eventually die, and that's where macular degeneration comes from. So we're proposing to fix that in exactly the same way that I described for atherosclerosis, and in the same, and we're actually doing just as well. We've already identified plenty of bacteria that can break down these materials, and plenty of genes that they have that allow them to do it, and we're introducing those enzymes into the mammalian cells too.
What about diet? Surely certain foods are going to...
Sorry, I can't hear what you're saying. Speak up.
Diet.
Yep.
Surely certain foods are going to be better at treating aging, who knows?
Okay, so the question is about diet, about whether one can substantially affect aging, the rate of aging, by eating well. And of course one can certainly accelerate the decline to age-related ill health by eating very poorly and getting seriously overweight and getting type 2 diabetes and such like, but you knew that already, so that's really not really what you're talking about. Other than that, if we start off, relative to people who are already looking after themselves reasonably well, and they're going to get to the age of 80 without too much trouble, my view is that actually no. There is essentially no evidence that we can make a significant difference by choosing, to eat a paleo diet or anything like that. It seems to me that from the data we have available, the differences that we can make by any such means, first of all, are pretty small, and secondly, they differ enormously from one person to another, because different people are pretty different in terms of what they can do. So my recommendation when people say, what can we do today, is, number one, pay attention to your body, just do what seems not to make you feel sick, that's pretty obvious. Number two, give me large amounts of money so that we can get these therapies developed a bit more quickly and increase your chances of being around to benefit from it. Go ahead.
Yeah, Aubrey, could you please comment on things like testosterone? I mean, for most people reading the newspaper on a Sunday, that seems to be men take testosterone and therefore they get rejuvenated. Is that
global accessory increase?
So the only word I really got in all that question was testosterone. All right, so yeah, the situation with hormone replacement and hormone supplementation is pretty much the same as for the previous question with respect to diet. And indeed, this also applies to any other type of supplements, vitamins and so on. You know, we need these things, but whether we need to supplement them and how we would benefit from supplementing them, again, the evidence is very, very tenuous that there's any significant benefit. And indeed, for many people, there may not be any benefit at all, in fact, for most people. So, no, it's definitely not going to be the elixir of life.
But that's for men. For women, it's a different story, however.
Okay, so Natasha points out very correctly that there is one aspect of hormone replacement therapy, hormone supplementation, which is very important, namely that in the case of women, after menopause, there is such a dramatic alteration in the production of certain hormones that replacing those hormones can have a substantially beneficial effect. Now, this is certainly true, but...
No.
Who's saying no?
I say no. Menopause is a natural part of life.
So the person without the microphone just said, menopause is a natural part of life. I don't think that entirely contradicts the fact that menopause causes a change in hormone levels and therefore causes things like osteoporosis, which I think is what Natasha was alluding to. Now, I'm quite sure that whether one wants to carry on having periods every month, one doesn't want to have loss of bone density and increased risk of fractures and so on. So, you know, you can say that some parts of menopause are a bit more desirable than others. But of course, when we come to the question of whether something being natural actually makes it desirable, we come to the topic of my talk tomorrow, about which I'll have plenty more to say about that general way of thinking tomorrow evening.
Aubrey, the problems that you're trying to solve, obviously you're going to have different rates of progress. Some will be more amenable than others.
Mm-hmm.
In terms of your definition of frailty, doesn't that mean that we'll still be frail because of some things? So it doesn't bother me that, you know, you can solve 4 of my problems if I still get Alzheimer's disease, then I'm still frail at that point.
Okay,
so is that true? And what is more likely to be solved earlier rather than later?
Yeah, so for any divide and conquer strategy for any particular technological problem, it is of course almost inevitable that some aspects, some components of the problem will be solved to the degree that one needs to solve them sooner than others. However, that doesn't really come into what I'm talking about. What I'm talking about is when we get to the point where we've solved all of these problems reasonably well. I don't think that we will see substantial postponement of age-related ill health until we implement all of the 7 types of fix that I mentioned reasonably well. We don't have to implement any of them perfectly, that's what I was talking about with regard to longevity escape velocity, but until we get all of them working reasonably well, we're just not going to see much benefit. So I just didn't address that precursor stage at all, because I don't regard it as really having treatments for aging until we get all of them working well enough to get at least a couple of decades of extra healthy life.
Aubrey, you talk about the 7 forms of damage, and you said that there haven't been any found in the last 30 years. Do you think it's possible or likely that if we manage to fix those, we'll find other ones that haven't manifested yet?
Excellent question. Will there eventually be 8th and 9th deadly things, so to speak? I think it's certainly possible that, I think it's very likely that we will continue to find new types of damage that fit into the 7 categories. That certainly has been happening at a respectable rate during the 30 years. Whether we'll find something that can really only be described as a new 8th category, and therefore that needs a radically different type of solution, rather than just a variation on things that we've already addressed, not sure. Probably we will eventually, but it could be an awfully long time. And even if we do, first of all, we've gained all the benefit in the meantime. Secondly, we're going to know about it in advance. There's going to be a lot of looking out for such things beforehand. So I'm not too worried about the possibility that something will suddenly kick us in the teeth, a long time in the future.
As a species, we're very young apes. Have you given any thought to where our genetic program takes us when we're 2 or 3 or 400 years old? What do we look like?
Right, so You use the phrase genetic program, and we've got to be careful about that. Our genetic program that we have determines the process of taking us from a one-celled zygote out to being an adult. But it's generally, in fact, pretty much universally accepted now within the research community who study aging that we do not have a program that does anything after that. I mean, there are certain things, of course, that go wrong in aging sooner than others. I mentioned menopause a moment ago as one example of that. But they go wrong through the lack of a program rather than through having a program. So, in other words, there's no real reason to suppose that we would look or feel or function any different if we could fix up this damage that accumulates as a result of the lack of a program, however long we live.
I have a question that, I mean, you mentioned longevity benefit as a side benefit of, but I mean, I think like when you say side benefit, it is like a negative connotation attached. I mean,
well, that's why I say side benefit rather than just side effect. I mean, I think that pretty much explicitly incorporates the fact that I think it's an extremely good thing.
Yeah.
Okay, that's all the questions.
Is that all we have time for? Okay, so of course, as I said, I will be around. Anyone who wants other questions, and I know there were lots of hands up still, please catch me later. Thanks.